If we revisit now the concept of generalized linear models, for this we need a vector of observations. So I have an observation of x1, of x2, of x3, ... up to xn. And I also put a 1 at the start to note that I've got one lot of the intercept term. And so for my observation vector, which I'm calling x, then I have this linear predictor nu, which I'm calling x transpose multiplied by alpha, beta 1, beta 2, up to beta n. So note the presence of the intercept term alpha necessitates the presence of the 1 at the top for one lot of it. I've then got a distribution that I'm modelling for y, and typically this will be something from the exponential family. And lastly, I need a link function that ties my x's to my y's. And so the link function here will be such that g of mu will be equal to this vector nu, where the mu is the conditional expectation, the expected value for the vector y given my set of predictors, the vector x. If I have a link function which is just g of mu is mu, then quite easily I'll have that the expected value of yi given xi is just the systematic part of a standard linear model, so the bit that doesn't have the residual error on the end. If I'm doing something a bit more complicated, like a Poisson regression, then I know the natural parameter for Poisson is the log of the mean. So in this case, I'd set nu, which is x transpose times beta, to be the natural log of mu. And similarly, I know that I can use the logit function, the natural parameterization, for a binomial regression model. We've already seen earlier in this subject how we can modify ordinary least squares, which was used to fit simple linear regression models where I had equal variance, uncorrelated residuals. How I could use the same ideas with a little bit of a tweak to fit models where I could relax those assumptions, or I had correlated errors like time series models or hierarchical models. And we've got a similar idea here. It's a little bit beyond the scope of this subject, but we can fit generalized linear models through doing what we call an iterated weighted least squares approach. So I'll give a little bit of detail on this, but it's a little bit beyond the scope of this subject to go into fully. The idea of this is that you get a weighted sum of squared residuals for some estimated parameters, and then you minimize those. And then based on that, you then recalculate the weights, recalculate the parameters, recalculate the weights, recalculate the parameters, and repeat until it converges. So whilst that sounds quite painful to do, well, it would be by hand, but modern computing packages can generally do that very, very efficiently. We do this through the score function, which is something we introduced previously, that the score function was just the gradient of the log likelihood function when differentiated with respect to the parameter, in this case theta. And we also saw that we have this nice property that the expected value of the score function should be 0. And we also introduced the Fisher information, being, broadly speaking, a measure of how much information there was about what the parameter estimate should be from a sample. And this was the variance of the score function, but we actually calculated it more by taking the negative of the expectation of the second derivative of the log likelihood. We can extend this idea up not to a single parameter, but to multiple parameters. I've actually called the multiple parameters here beta 1 to beta n, although one of those could be an intercept parameter if I set the corresponding observation in the x to be locked to be a 1. But if I've got n parameters to estimate, then I've got this vector here. So all I would do then is I'd define the score not just as the derivative with respect to the parameter, but the sum of the derivative with respect to each of the parameters. So d by d beta 1 of the log likelihood plus d by d beta 2 of the log likelihood, and so on. So if you're familiar with the Nabla notation, then you can also write it as that. For the link function, if I've got the link function nu being x transpose beta, then I will get the score v beta with x v nu. And if I use the matrix chain rule, then I can simply get this in terms of the Fisher information, that the Fisher information associated I of beta will be x times the Fisher information I of nu times x transpose. If we take the Newton-Raphson method, which I hope you've seen before, it's a relatively common procedure in numerical methods. And what it is, it's concerned with finding numerically the value of x for which some function f of x equals 0. So pictorially, if my function f of x is this blue curve, I want to estimate the point circled in red such that f of x equals 0, which x gives that value. The way this is done is we start with a guess. We think x is about x0. So I pick a point x0, and I approximate the function f with a linear function, which has the same gradient to that point. So it has gradient f dashed of x0, and which goes through the point x0, f of x0. And then I solve to find when it equals 0, when this linear approximation equals 0. And hopefully it'll give me a value which is closer to the real point. I'll call my new guess not x0, but imaginatively I'll call it x1. So if I solve the linearized approximation on the second dot point, then I'll get x1 to be x0 minus f of x0 divided by f dashed of x0. So pictorially, it's approximating the function at x0 to a linear function, which meets the curve at f of x0 with gradient f dash of x0, and it just extends the line down until it meets the axis. So in this case, x1 is closer to the true root of the equation f of x is 0 than x0 was. And then repeat that again, repeat that again, repeat that again, and in this case it will be getting closer to the real solution. So something like that. And keep repeating until I'm satisfied that it's converged. Now this is the same idea with Fisher scoring, where I estimate the weights, then I estimate the parameters, then I use those to estimate the weights, then use those to estimate the parameters repeatedly. So if we think of the analogy to the Newton-Raphson method, albeit a lot more complicated, and as I said, beyond the scope of the subject. So I maximize the likelihood by when the expected value of the score function is 0. So I'm basically finding a root a bit like the Newton-Raphson, finding a root of when some function is 0. So all I need to do is just keep going around this with new estimated weights, a bit like finding a new estimated sort of gradient for my Newton-Raphson. and keeping going until I'm converging on a value. So you can see these look a lot like the Newton-Raphson ones. So if I start with a single variable and an initial estimate, then what I will get to here is that my new n plus 1 is new n plus the score of x at new n divided by the Fisher information associated with x given my new m. So it looks very similar to Newton-Raphson. And again, I'll just repeat that until my new m plus 1 and my new m are not moving far once it's converging on fixed values. What this does mean, though, is that I said this was great and we had all of these modern statistical tools that could fit these models without us having to do the, quite frankly, awful numerics on this. But what it's aiming to do is it is maximizing likelihood, because anything to do with Fisher information is based on likelihood, and so we are effectively maximizing the likelihood at each turn, or so we think. My slight buyer beware is this example. If I take a Poisson variable and I say I've observed 3 realizations of this Poisson, Q1 is 1, Q2 is 2, Q3 is 1.5, then if I just blindly follow the methods I've said before, it would fit it saying, oh look, I'm fitting a Poisson and the mean of the observations is 1.5. Nothing wrong with that at first glance, because I could have 4 observations of a Poisson with mean 1.5. I could have a 1, a 2, a 2, and a 1 with mean 1.5. However, of course, I cannot observe 1.5 from a Poisson. It's a count variable, so I can observe 1s or 2s or 3s, but never 1.5. But if I just tell it that, its link function only knows it's linking to a function of the mean, and for Poisson it's the case of the natural log of the mean. So if I actually just blindly give it this data, it will fit and it will give me estimates of the fits for this Poisson regression model. Now, it's based on a likelihood or a maximum likelihood procedure, but in fact the likelihood of ever observing 1.5 in a Poisson is 0. So the model fit it'll produce the estimate very efficiently through things like Fisher scoring, but the fit will in fact be garbage. It'll be meaningless, because these things don't necessarily look at the individual observations and say what's the likelihood of each observation. It just says, oh, I'm fitting this through this numerical procedure, the mean of my observations is this. For a Poisson regression model, I'm fitting using link function with the log of the mean. There's your answer. So, as I say, modern statistical procedures are both a blessing and a curse. They're very efficient ways of fitting models, but you need a good statistician at the back end to check that the models you're fitting make sense.